Your leg is on fire, not from heat, from venom. A brown recluse has just bitten you in your sleep, and over the next several hours the skin around the bite will start to die. Not bruise, not swell, die. Tissue turning black and sinking inward, while doctors debate whether to cut it out before it spreads. This happens. It is documented, photographed, published in medical journals you would not want to read before dinner. Now picture the opposite kind of bite. A funnel web spider, the kind that lives in backyards outside Sydney, delivers venom so fast-acting it can drop a grown man in under an hour. Before 1981, when the antivenom finally arrived, that bite killed. Not maybe, not rarely. It killed with a reliability that made emergency rooms treat every single bite as a countdown. You already knew spiders were dangerous. That is not the surprising part. Here is the surprising part. The animal you are more afraid of than sharks, snakes, and wildfire combined is, right now, quietly doing more to keep you alive than almost anything else on this planet. Today, we are going to find out why the creature you would kill on sight, without a second thought, is the one thing standing between you and a world that would eat itself alive without it. Go back roughly 380 million years. No flowers yet, no birds, no mammals, no dinosaurs, not even proper forests as you would recognize them. Just towering ferns and the first tentative reptiles crawling out of swampland. And already, in that world, there were creatures spinning silk. Not modern spiders exactly, but close enough that the lineage is unmistakable. 8 legs, venom, silk glands, the whole toolkit already assembled, while the rest of life on Earth was still figuring out how to walk. Sit with that for a second. The blueprint that produced the thing curled in the corner of your garage right now was already finished before trees had bark as we know it, before the supercontinent Pangaea had even fully formed, before anything on this planet had a spine strong enough to stand upright. And then came the part that should have ended everything. Around 252 million years ago, the planet tried to erase almost all of it. Scientists call it the Permian extinction, though people who study it privately call it something closer to the Great Dying, because that is closer to what actually happened. Volcanic eruptions on a scale hard to visualize, poisoning the atmosphere for what may have been close to 1 million years. Oceans turning acidic, oxygen levels collapsing. By the time it was over, somewhere around 90% of all species on Earth were gone. Not endangered, gone. It remains, to this day, the worst extinction event this planet has ever recorded. Worse than the one that killed the dinosaurs. Worse than anything since. Spiders made it through. Not unscathed, not untouched, but the lineage held. Somewhere in the wreckage of a dying world, silk-spinning survivors kept spinning, kept hunting, kept reproducing in whatever scraps of habitat the catastrophe left behind. While roughly 9 out of every 10 species on the planet vanished forever, the ancestors of the thing you swat off your windowsill were quietly rebuilding. That would be a remarkable enough story if it only happened once. Fast forward past the Permian, past the rise of the dinosaurs, past 200 million years of a planet dominated by reptiles the size of buildings, to 66 million years ago, an asteroid roughly the width of a small city strikes what is now the Yucatan Peninsula, with the force of billions of nuclear weapons detonating at once. Firestorms circle the globe. Dust and sulfur block out the sun for what researchers estimate could have been years. Photosynthesis stalls. Food chains collapse from the bottom up. Every non-avian dinosaur that had ever walked the Earth, gone, in what is, geologically speaking, an instant. And once again, in the ash and the dark and the cold, spiders held on. This is not a coincidence you can wave away. 2 of the worst mass extinctions this planet has ever experienced, separated by roughly 186 million years, and the same basic body plan, 8 legs, venom glands, silk production, walked out the other side of both of them. Whatever spiders are doing, structurally and behaviorally, it is not fragile. It is not a fluke of good luck repeated twice. It is something closer to a design that simply does not break easily, no matter what the planet throws at it. Today, that lineage has fractured into something staggering. Taxonomists have formally described more than 50,000 distinct species of spider, and new ones are still being logged every year. Researchers estimate the true number in the wild could be significantly higher, Some guesses running past 120,000 once undiscovered species are accounted for. They live on every continent except Antarctica, in deserts where almost nothing survives the heat, in caves that have never seen sunlight, underwater, in the case of the diving bell spider, which builds an actual air-filled dome beneath the surface of ponds and lives inside it like a submarine. On mountain slopes above 5,000 meters, where the air is too thin for most insects to fly. This is not an animal clinging to survival in one narrow, lucky corner of the world. This is an animal that appears to have solved nearly every environment the planet has to offer, using more or less the same basic anatomy it arrived with hundreds of millions of years ago. And here is the detail worth sitting with before we go further. Persistence like that is never an accident. Nothing survives two planetary-scale catastrophes and then diversifies into 50,000 forms purely by chance. When something in nature endures that consistently, across that much time, through that many independent extinction filters, it is usually because that something is doing real work, load-bearing work, the kind of work an ecosystem quietly depends on and rarely notices, right up until it is gone. So what does that load-bearing work actually look like, in practice, on an average day, on an average patch of ground somewhere near you? In 2017, two researchers named Martin Niffler and Klaus Birkhofer decided to actually run the numbers. Not estimate loosely, calculate. They pulled together data from spider studies across forests, grasslands, deserts, and croplands on every inhabited continent, then modeled the total biomass of spiders alive on Earth at any given moment, and what that population would need to consume to sustain itself. The total mass of all the spiders alive on the planet at once, they calculated, comes out to somewhere around 25 million tons. To put that in perspective, that is heavier than the combined weight of every human being currently alive on Earth. Now here is the number that actually matters. To sustain that much living tissue, the global spider population consumes somewhere between 400 million and 800 million tons of insects and other small prey every single year. Read that range again, because it is not a typo and it is not exaggerated for effect. It comes directly from the published estimate. The low end of that range alone is comparable to the total amount of meat and fish consumed by the entire human species annually. The high end is double it. Every mosquito that never bit you, every fly that never landed on your food, every crop-destroying moth that never got the chance to lay its eggs on a field of wheat. Multiply that by hundreds of millions of tons, repeated every year, on every continent except one, and you start to understand what ecological pest control actually means when it is not a slogan on a nature documentary, but a load written directly into the planet's food web. None of this happens where you can see it. That is the part worth sitting with. This is not a service performed in a laboratory or announced at a press conference. It happens in silence, in the dark, in the gap between one blade of grass and the next, executed by an animal most people will not walk past without flinching. The scale of it is almost inversely proportional to how much credit it gets. And the usefulness does not stop at pest control, it extends somewhere far stranger, into the venom itself. The same substance that opened this documentary with a dying leg and a countdown to hospitalization. Researchers at the University of Queensland spent years studying the venom of the very funnel web spider responsible for that fatal bite. Inside it, they isolated a peptide called Hi1. In laboratory and animal studies, that peptide showed something remarkable. Injected after a stroke, it appeared to protect brain cells from the cascade of damage that normally follows when blood flow is cut off, extending the window in which brain tissue can potentially be saved. The exact same chemistry engineered by evolution to kill a human being in under an hour is now being studied as a way to preserve a human brain in the minutes after catastrophe. That is not an isolated case. Tarantula venom contains a compound called Protex-2, which binds with unusual precision to a specific sodium channel in human nerve cells, one directly linked to how the body registers pain. Pharmaceutical researchers have spent years trying to exploit that precision, hoping to build a new generation of painkillers that block pain signals directly at the nerve, without touching the opioid receptors responsible for addiction and overdose. The very toxin engineered to paralyze prey is being taken apart. piece by piece, in the search for a safer alternative to one of the deadliest drug crises in modern history. Numbers on a page are one thing. What happens when you actually remove the spider from the equation is another. And unlike most ecological warnings, this one is not hypothetical. It already happened, it was measured, and it happened on a scale large enough to threaten the food supply of an entire region. The setting is the rice paddies of Southeast Asia, starting in the 1960s and accelerating hard through the 1970s. This was the era of the so-called Green Revolution, when new high-yield rice varieties and modern chemical agriculture were being rolled out across Indonesia, the Philippines, and much of the surrounding region, promising to solve hunger at a scale never before possible. Part of that package was heavy, routine use of broad-spectrum insecticides, sprayed not occasionally but on a fixed calendar, whether or not pests were actually present in a given field. The logic seemed sound at the time. Kill the insects, protect the yield. What almost nobody accounted for was what else lived in those paddies. Rice fields, it turns out, are dense with spiders. Wolf spiders hunting along the muddy banks. Orb weavers strung between the rice stalks. Lynx spiders lying in ambush on the leaves themselves. In an undisturbed paddy, these populations sit at the top of a tight, fast-moving food web, and their primary prey happens to be one of the most destructive rice pests on the planet, the brown plant hopper, a tiny sap-sucking insect that can, left unchecked, wipe out an entire field in weeks by draining the plants dry and spreading disease between them. Under normal conditions, the spiders keep the plant hopper population suppressed simply by doing what spiders do. Constant, quiet predation, day and night, invisible to a farmer walking the field. But broad-spectrum insecticide does not distinguish between the pest it is aimed at and the predator quietly controlling that pest. It kills both. And here is the part that caught agricultural scientists off guard. The plant hopper population recovered from a spraying far faster than the spider population did. Plant hoppers breed explosively, generation to generation measured in days. Spiders, by comparison, take weeks or months to rebuild a population and rely on that time to lay egg sacs, hatch, mature, and resume hunting at any meaningful scale. So the sequence that played out, field after field, season after season, went like this. Spray the paddy, kill the plant hoppers, also kill the spiders. Watch the surviving plant hoppers rebound within days into a population with almost no natural predator left standing to slow it down. Entomologists gave this phenomenon a name, pest resurgence, and by the late 1970s, it had become one of the most well-documented failures in modern agricultural history. Fields that had been sprayed to protect their yield were, in a number of well-recorded cases, ending up with worse plant hopper outbreaks than fields that had barely been sprayed at all. Researchers working with the International Rice Research Institute in the Philippines, most notably in surveys led by entomologist Peter Kenmore during the early 1980s, traced the mechanism directly back to this predator collapse. It was not a mystery requiring speculation. Field data across multiple growing seasons showed the same pattern again and again. Heavier insecticide use correlated with lower spider counts, and lower spider counts correlated with worse plant hopper outbreaks, not better ones. The chemical meant to solve the problem was, in a very literal and measurable sense, manufacturing the very crisis it was supposed to prevent. By some estimates from that period, plant hopper-driven crop losses tied to this resurgence effect reached into the millions of dollars across the region in a single bad season, and in parts of Indonesia, entire fields were lost outright, forcing replanting, or in the worst cases, total crop failure for the farmers who depended on that harvest to feed their own families. This was not an abstract ecological imbalance discussed in a university seminar. It was rice not reaching a plate. The response, once the pattern was understood, tells you almost as much as the collapse itself. Beginning in the mid-1980s, agricultural programs across the region, most visibly a large-scale farmer education initiative backed by the Indonesian government and the Food and Agriculture Organization, began actively teaching farmers to scale back routine insecticide spraying and instead monitor pest levels directly, spraying only when genuinely necessary, specifically to let natural predator populations, spiders chief among them, rebuild and do the job the chemicals had been doing worse all along. Indonesia's national program, launched in 1986, cut insecticide use dramatically nationwide within just a few growing seasons, and plant hopper outbreaks measurably declined as spider populations recovered in the fields left unsprayed. Let that sit for a moment, because it is the cleanest version of this documentary's entire argument playing out in real agricultural data. Farmers spent years trying to engineer around a predator they saw as irrelevant, or worse, as just another crawling nuisance sharing their field with the pests they actually cared about. The fix was not a better chemical or a stronger dose. The fix was, in large part, backing off and letting the spiders come back. So go back to that leg, the one from the very beginning of this, black at the edges, tissue dying beneath the skin, a doctor deciding how much to cut away. That was real. It is still real. Somewhere tonight, that exact scene is playing out in an emergency room, and nothing in the last 3 chapters undoes it. That is the part worth being honest about before this ends. This was never a story about a misunderstood creature that turns out to be secretly friendly once you get to know it. The venom is still venom. The bite still does what a bite does. A funnel web spider that wanders into the wrong backyard has not become less dangerous because researchers found something useful in its chemistry. Danger and usefulness are not opposites here. They are the same substance, looked at from 2 different rooms. What has changed is what happens after the danger. Right now, in laboratories on more than one continent, that same funnel web venom, the kind that used to kill with near total reliability before 1981, is sitting in vials being tested not as a threat, but as a treatment. Early-stage trials building on the high-wonder research are pushing toward human applications for stroke recovery, chasing a longer window to save brain tissue after blood flow is cut off. It is not finished. It is not approved for use in a hospital near you. It may still fail, the way most promising compounds in early research eventually do, but it exists, actively, right now, moving through the same pipeline that turned other venoms, other toxins, other things humans use to simply fear, into medicine cabinets. The silk story is not finished either. Labs experimenting with recombinant spider silk proteins are still chasing a version that can be manufactured at real industrial scale, cheaply enough to replace materials that pollute far more to produce. Nobody has fully cracked it. Every year brings a new claim, a new prototype fiber, a new startup insisting they have solved what spiders solved on their own several 100 million years ago without a laboratory, a patent, or a funding round. And that, maybe, is the honest note to end on. Not that spiders are good. Not that the fear was wrong all along and you should feel foolish for flinching at the one in your bathtub tonight. The fear is not wrong. It is just incomplete. It is the reaction of a brain that only had time to register the danger in front of it, not the several 100 million years of history behind it. Not the millions of tons of insects quietly not landing on your food tonight. Not the vial in a lab somewhere that might, eventually, help someone survive a stroke. Spiders were not built to be liked. They were not built to be feared either. They were built, however many 100 million years ago, to do a job, and they have been doing it through every catastrophe the planet has thrown at them since. Whether that makes them something to root for is not really the point. It never was. The point is that the world you are standing in right now, the one with food still on the shelves and diseases still held back a little longer, was built with them in it, not around them. So the next time you find one in the corner of a room, notice the flinch. That is fine. That is honest. Just know it is not the whole story anymore. If this kind of thing is your speed, the animals nobody defends, told with the receipts to back it up, there's more coming. Subscribe if you want the next one. Drop a comment with the creature you think deserves this treatment next. And if you know someone who still stands on a chair over a spider in the bathtub, this one's for them.